Okay, hello everyone. Good afternoon. So this week we are going to review how electrons in conduction bands are distributed out as a function of energy. Okay, so before getting into some more great details for today's lecture, I will briefly review what we have learned last week. Let's go back a few slides more. Okay, so please turn off your microphone because let me double check just in case. So last Thursday we had some technical issue while I was streaming out my lecture. So if you have any problem or troubles in joining my online lecture, please raise up your hands. You can use those functions or leave your text message. Then my TA is going to check your text message and I will be notified within a couple of minutes. So if you have any problem to listen to what I'm saying, please raise up your hand or leave your text message in the chatting window. Then we can do our best to address your technical issue. And that issue will be recorded in this movie clip. So many your classmates who unfortunately didn't participate in today's lecture had a trouble in listening to my recorded lecture by the end of this week. So please uh, leave your text message if you have been faced with any technical issues while joining my online streaming lecture. All right, so let's review what we have learned last week. See, I asked you to remember those important constant values. Not if possible. I guess it is kind of mandatory. As a device engineer, please remember those numbers that will be quite often used while you are studying all the lecture slides. And herein, we have illustrated how dopant atoms are ionized within a silicon crystalline material in energy band diagram. So depending on the temperature, how dopant atoms are ionized and how newly created free electrons and free holes are existing in conduction band and valence band respectively. And herein we try to draw a figure showing electron concentration N divided by N sub D doping concentration as a function of temperature. So as temperature increases, N over ND becomes 1 in the end. And later on, maybe at 450 Kelvin, the number of electron is way higher than the dopant atoms. In other words, the silicon material becomes intrinsic. I mean, the impact of doping has been lost if temperature is too high, such as 450 Kelvin or higher. And all the mechanism, how dopant atoms are first frozen out and then, be awakened to emit out a free electrons into the conduction band. And in the end, all the, electron hole pairs are created. The number of electron hole pairs are way higher than the free electrons coming from the dopant atoms, so that silicon material becomes intrinsic. And we have learned how the electron's kinetic energy and hole's kinetic energy in the conduction band and valence band. So once electron has sit on an energy state which is slightly away from the conduction band edge, E sub C, then which means physically that electron has much more energy compared against the electron sitting on at the edge of the conduction band, such as E sub c. So the energy difference herein indicates how much kinetic energy a single electron has. And similarly, you may understand how much energy this hole has compared against the hole sitting at the edge of the valence band E sub v. So this energy difference indicates the hole's kinetic energy. All right. And thermal equilibrium wise, no external forces are applied, then we can claim that this material, this wafer, this product is at thermal equilibrium. So more specifically, if there is no externally applied electric field and no magnetic field and no mechanical stress and even no light, then we can claim that there is no external force, which means this sample is exposed at thermal equilibrium. And one more thing that I have stressed out is a dynamic situation instead of static situation. So whenever you're imagining imagine the situation, the thermal equilibrium, the word of the thermal equilibrium, how does it look like? Maybe everything is very calm and sit down and stable, but in silicon crystalline material, that is not true. A lot of electrons, say per cubic centimeter, 10, 10 to the 10. So 10 billion free electrons are already available, so that those electrons are, recombined with the free holes. And at other location within a silicon crystal material, a newly created electron pairs are generated together. So at a certain region, electron has annihilated. In other words, an electron is killed with holes, but at the other places in a silicon material, new holes are created. So in terms of total number of free electrons and free holes in a silicon material is no change. However, which electron was there, is there, will be there, we cannot guess. We cannot answer this electron will be available forever. That is wrong answer. So in that sense, you may understood what the dynamic situation is. Okay. So herein I described that every process happened in silicon material is well balanced by its inverse process. So for example, electron hole pairs are created, but at the other places electron hole pairs are recombined together. So the total number of electron holes are always uh, maintained. And the thermal agitation or electron holes exchange energy to each other, even here in with crystal lattice. So electron holes are roaming around within a silicon crystal material. So in terms of how those carriers, such as electron holes, are exchanging its energy to whom or to who? Well, uh, it is always exchanging its energy with counterparts, electron against the hole against the electron. But that's not always true. Electron holes are exchanging its energy with silicon atoms itself. Okay, so herein with the crystal lattice. All right. And the Fermi function. So last lecture, I mentioned that the role of Fermi function is, you know, to give us some idea, to give us the number, how likely a energy state is filled with electron. So suppose that there is a single energy state, which is empty, vacant, and at some point, at a certain time, electron hole pairs are created, and an electron from the electron hole pairs would like to sit down or to fill out the empty energy state that I have just mentioned, then how likely it is happened? what is the probability for the electron to be filled in the empty energy state in conduction band? That's a very tricky question at a first glance. It is hard to tell. However, with the help of Fermi function, you may simply answer this question, because the Fermi function indicates the probability that an available energy state or an empty energy state is occupied with electron. So last week we plug in a certain energy value that was a Fermi energy level, right? So here in E, instead of E, plug in the E sub F. Then here in, you're gonna plug in the E sub F. Then you may do simple mass calculation, 1 plus exponential EF minus EF over KT. So exponential to the 0. So 1 plus 1, 2, right? So 1 over 2. In other words, 50%. So any energy state, but a very specific energy state which has an energy level of Fermi energy level, the probability of finding an electron at the Fermi energy level is exactly 1/2 or 50%. Okay? So in that sense, Fermi function gives us an idea how likely an empty energy state is filled with electron. So maybe intuitively, you may answer this question. What is the probability of finding an electron in valence band? As you have learned, valence band is almost, not all, almost filled with electrons, so that the probability of finding an electron in any energy state available in the valence band is almost 1, right? Not 100%, but almost 1, maybe about 99% or 99.999%, because the valence band itself has been almost filled with many free electrons. Okay, well, definitely that not free electrons, the electrons which has been used to build up the covalent bonds between two neighboring silicon atoms. Okay. All right, so we have learned the physical meaning of the Fermi function, and we have practiced how the Fermi function has been drawn depending on the temperature. So at 0 Kelvin temperature, the step-like function has been used to draw the Fermi function curve shape. And as temperature increases from 100 Kelvin to 400 Kelvin, the Fermi function has been, tilted a lot. So this less steep slope can be found in this figure. Okay, and again here, notice that once energy is equal to the E sub F, here in the X of 0, the Fermi function value is 0.5, 50%. So the physical meaning of Fermi function is the probability value of finding an electron at the energy level, having a Fermi energy level, is 50%. Okay. And lastly, we have briefly learned what the Boltzmann approximation was. So the energy level that we are interested in is slightly higher than the Fermi energy level by 3 times kT. Again, the kT at room temperature 26 milli electron volt. Okay, so it's 3 times 26 milli is how much is 78 milli electron volt. So if the energy level that I'm interested in is slightly higher than the Fermi energy level, the Fermi function, very complicated form of Fermi function that we have learned here in, take a look at here, 1 over 1 plus exponential power, which looks complicated even in terms of when you are doing the integration work, it is not easy to estimate any. Let's see. Suppose that in calculus class, say that 1 plus exponential x dx. Can you do by hands solve this integration problem? That is not easy, but this equation is quite simple, right? So this 1 plus, so this term is kind of, troublemaker when you are solving this integration problem. So in that sense, Boltzmann approximation is very strong because if the energy level is satisfied with this if condition, then the Fermi function can be simply written as exponential to the something, okay? Which should make our life much easier whenever we are solving the integration problem. And if the energy level that we are interested in is slightly lower than the Fermi energy level, at least by 3 times kT, then Fermi function can be rewritten and approximately written as 1 minus exponential something. So instead of, the original form was 1 over 1 plus exponential something, but now it is 1 minus exponential something. So if you're faced with this type of, integration problem, you may solve this problem by hands. If x exponential dx, you may solve this problem as well. Okay, so in the sense, Boltzmann approximation is very strong, and we're gonna use it definitely when we are estimating how electrons in conduction band, how the electrons in conduction bands are distributed out as a function of energy of electron. So in energy band diagram, how many electrons can be found at this specific energy level? How many electrons are available at this specific energy level? This is question. Previously, for the last 1 month, we have learned the total number of electrons can be modified, in n-type silicon material, depending on the doping concentration into the silicon material. We can modify the total number of free electrons, okay, in the unit of per cubic centimeter. But here, my question is not this, but N of E. Depending on the energy level, I'm interested in this energy level. How many electrons having the energy level, say E sub 1, are available in conduction band? Well, if you can write down any analytical equation for N of E, then if you sum N of E for all the energy level in conduction band, maybe from E sub C to energy's top energy of conduction band, then once you do integration work, then the answer would be N, right? So previously we have learned how to estimate the total number of free electrons in silicon materials. However, from now on, I will try to find out the analytical equation for N of E, the number of electrons as a function of energy, especially in the conduction band. All the energy state, how many free electrons can be existed? That's the question, okay? So today, let's solve this problem. The answer can be found on the right-hand side, carrier distribution herein, that energy of electron. Let's move on this. So energy of electron, and the x-axis here indicates the number of electron as a function of energy. This is energy. Okay, so this is kind of y-axis. This is kind of x-axis. So the answer is this. Once at energy is equal to conduction band H E sub C, no electrons available. But if you slightly increase your energy level that you are interested in, the number of electron is quite high, a lot. But if you go up more, the number of electrons is exponentially decaying, so exponentially decreasing a lot. Okay, So here, physically, most of the electron will be available near to the conduction band edge. Okay. So intuitively, you may guess in conduction band, there are 10 to the 10 per cubic centimeter electrons available. 15, because the doping concentration is 10 to the 15 is more conventional and reasonable, typical. Then, please turn off your microphone, please. Then, the total number of electrons that we have already known, depending on the doping concentration. However, the question is how many electrons can be found at a certain energy level in conduction band? It's a very tricky question. So for that purpose, we should obtain the N of E. Okay? So here in this lecture note, the answer can be found. How to obtain the N of E, electron concentration as a function of energy, multiplying G sub C of E and F of E. So what was this Fermi function? And what was this density of state? So last week I brought an analogy how to understand electrons in conduction bands are distributed out. What was this? The baseball stadium. Okay, so the how the seats are designed, that is already set up. Okay, we cannot change the position of the seats in baseball stadium, but it is hard to guess which seats will be taken by the audience or by the people, baseball fan. So that is a tricky question. So big data analyst has used to record how many seats are available and how many baseball fan has taken the seats over 24/7. I mean, for a year, they have recorded how people's are taking their own seats. Then they can get the probability value of each probability value of finding a single person in each seat in baseball stadium, which is quite similar work that we would like to look for. Here in conduction band, we are looking for a engineering solution, N over E, the electron concentration as a function of energy. How to approach this problem. The first step is we should understand how energy states are distributed out in conduction band. So as we have learned, density of states give us the hint, right? Per unit energy per cubic centimeter, how many energy states available are existing in a silicon crystalline material. So that we can use density of state, which is kind of an analogy of how seats are designed and set up and placed in baseball stadium. Then Fermi function. Fermi function, as we have just learned, the probability value of finding an electron at a certain energy. So Fermi function can give us the value of the probability of finding an electron at an energy. What is the analogy, matching analogy happened in baseball stadium? Yeah, the big data guy has recorded how the people are taking their own seats over a year. Then they can estimate a single seat in baseball stadium is taken by a person for, with the probability of 1%. And that is kind of Fermi function for baseball stadium. With that information can be used to, to have a reasonable, the highest ticket cost. Okay, going back to the silicon material, the Fermi function, we know Fermi function and we know the density of state in conduction band. Now we are almost geared up with density of state Fermi function to look for the energy the electron concentration, NOV, as a function of energy. So let's take a look at the great details on the bottom side. So here is energy band diagram for silicon material. Here E sub C, E sub V, okay, conduction band H. And now it is the Fermi function has been defined, I guess, in the mid gap of the energy band diagram. Okay. In other words, this silicon material is, undoped. There is no dopant atoms included in this silicon material because the Fermi energy level is well balanced within a band gap energy level. Okay, and on the second left-hand side, you can see that the density of state. So here in the y-axis indicates energy of electron, and x-axis indicates the density of state, G sub C of E, which means the conduction band's density of state. So previously we have learned that there are kind of complicated equation, but you may remember this is square root E minus E sub C and a certain coefficient. So the curve shape is like that, right? This is kind of y square root x. This is y, this is x, okay? All right, and similarly, you may draw the density of state G sub V of E, because it is a certain coefficient times EB minus E. So this is y, this is x. Again, the energy of hole. Minus y direction indicates increasing energy for holes. Okay, right. So now we are ready. We have fully understood how states are distributed out in conduction band and valence band respectively. And now these empty energy states, well, if we as energy level increases up, more energy states are available. The number of, this value from here to here, this value indicates that the more energy states are available in conduction band. However, as energy increases, the probability of finding an electron at such a higher energy level is almost zero, right? So this value indicates f of E. The probability value is here 0, and here is a conduction band edge. So beyond the conduction band energy level, many energy level are available, but in terms of the probability of finding an electron is almost 0. Okay, so many states, empty states available, but probability value is very low. Okay, so now the final destination that we are going to is NOV. So to estimate the number of electrons at each energy level, the first question is how many energy states are available, and then how likely those energy states are filled with electrons. If we are still trouble in understanding this concept, suppose that there is a 3 empty states, empty chairs, and each chair has a 1/3 probability of finding a person. So that is the probability of finding a person is 1/3. That is 1/3. Then, in general, maybe for a given 3 chairs, how many person you can find out, because each chair has identical, probability of having a person. So 1, 2, 3. So at least 1 out of 3 should be filled with a person. Okay, so now here at this energy level, suppose that this chair has been placed on the 31 first floor of an apartment. Then the energy level of this energy for those 3 chairs is quite high. For given energy level, 1 out of 3 is filled with person. How did you know that? At least density of state, you should know. At 31 first floor, 31st floor, there are three chairs. That information can be obtained from the density function. And how come you have well guessed? Only single chair is filled with a person. Because you know the probability value, right? So uh, here in three chairs available, this is kind of density of state. And the probability is a 1/3. So one person can be found. So that's the reason why you should do the multiplication work, right? So density of state times the probability. Then we will get how many electrons, how many people at a certain energy level can be found. Okay? So N over E, we can obtain it by multiplying density of states and the Fermi function. Okay, let me erase all inks in this slide and then take a look at this two curve at an energy level of E sub C. So it is increasing. Here, the curve is decreasing. It's hard to draw because it's too small. A certain value is increasing times certain value is decreasing. And what kind of curve shape you're gonna get? Definitely increasing and decreasing. Okay, so take a look at this figure and curve shape, right? Here, energy direction indicates N over E. Okay, N over E is obtained the G sub C of E times Fermi function. Okay, so you will see that the curve shape should be increasing afterwards, decreasing. So physically, you can guess that at a certain energy level, the number of free electrons should be peaked. Okay, and can you guess what that energy level is to give us the highest number of electrons at a certain energy level? This energy difference, E minus E sub C. Say this is, how to say, what's we call it? Just one E1. E1 minus EC. What is this value? The answer is KT over 2. Can you estimate how come KT over 2 can be obtained? It's very easy question. Let me give you a hint. My question is, at which energy state the total not total, the number of electrons available at this corresponding energy level is peaked, has the highest value? Well, once you know the equation of N over E, take a derivative of D of E with respect to the energy. And once this slope is 0, then you will get the energy value. If you do some math, you will get KT over 2. Here the question is how to write down the analytical equation for N of E. N of E is G sub C times F of E. You can plug in each equation for each term. Then you can do that. But that's not easy job because of this guy. 1 over 1 plus exponential E minus EF over KT. That is not easy. So you should use Boltzmann approximation. Okay. All right. That's all for how the electrons are distributed out in conduction band for undoped silicon material. The answer was most of the free electrons in conduction band would prefer to stay near the conduction band edge. Okay, that was a small conclusion. So I guess it is now 12:35. So I'd like to take a short break. I will get back to you at 12:45. 10 minutes break time. So see you soon. 12:45.
이 미팅은 녹화되고 있습니다.
Okay, I'm back. Network issues.